Before searching for the answer, we need to understand one important thing. When asking how much the Earth weighs, in everyday life, we usually use the word weight to mean mass, but in physics, weight and mass are two different concepts. Mass is the amount of matter contained in an object. It hardly changes whether that object is on Earth, on the moon, or in outer space. Weight, meanwhile, is the gravitational force acting on that object. Therefore, a person with a mass of 60 kilograms on Earth still has a mass of 60 kilograms on the 60 kilograms. Moon. But that person's weight on the moon will be much smaller because gravity there is weaker. The same applies to Earth. If speaking precisely, we are asking what the mass of the Earth is, because the Earth is not standing on any scale. It is floating in space, orbiting the sun, and rotating around its own axis. There is no floor beneath it to measure its weight in the ordinary way. What we can determine is the mass of the Earth, meaning the total amount of matter that makes up this planet. And that amount of matter does not only include the ground beneath our feet. It includes all the mountains, oceans, deserts, forests, the atmosphere, the crust, the mantle, oceans, deserts, forests, the atmosphere, the crust, the mantle, the molten outer core, and the solid inner core lying thousands of kilometers beneath the cell. Surface, all of those things combined create the enormous mass of the Earth. But the problem is that we cannot dig up the entire Earth to weigh each part. Humans have only drilled a little more than 12 kilometers deep, while the Earth's radius is more than 6,300 kilometers. That means most of the planet still lies beyond our direct reach. So how can we know the total mass of an object that we cannot fully touch? The answer begins with a phenomenon that everyone experiences every day. Everything falls to the ground. Drop a stone from your hand, it falls. Jump off the ground, you will fall back down. Observe rainwater, an apple, a marble, or any object around us. All of them are pulled toward the Earth. That invisible pulling force is gravity, and gravity itself is the key to weighing the entire planet. In the 17th century, Isaac Newton proposed the law of universal gravitation. According to this law, all objects with mass attract one another. You attract the Earth, and the Earth also attracts you. A book attracts a table, and the table also attracts the book. But because the masses of ordinary objects are too small, the force between them is almost impossible to feel. The Earth is different. It has an enormous mass, so its gravitational pull is strong enough to keep us standing on the surface, keep the oceans from flying into space, and keep the atmosphere surrounding the planet. Newton showed that gravity depends on two factors: the masses of the objects and the distance between them. If we know how strong gravity is, know the radius of the Earth, and know the gravitational constant, we can calculate the mass of the Earth. It sounds simple, but for many centuries, one of the most difficult quantities to measure was the gravitational. Constant gravity between small objects is extremely weak. Two balls placed next to each other also attract one another. Two balls placed next to each other also attract one another. But the force is so small that it cannot be felt by hand. Therefore, to measure it, scientists needed extremely delicate experiments, and one of the most famous experiments in the history of science was the experiment that helped humanity weigh the Earth for the first time. At the end of the 18th century, scientist Henry Cavendish conducted an extremely delicate experiment. He did not use a giant scale, did not climb a mountain, nor dig into the ground. Instead, he used a device called a torsion balance. This device consisted of a very light horizontal bar with two small spheres attached at both ends. The horizontal bar was suspended by a thin wire. Near the two small spheres, Cavendish placed two large lead spheres. The idea of the experiment was very bold. If all objects with mass attract each other, then the two large lead spheres would attract the two small spheres. This force was extremely weak, so weak that it only caused the horizontal bar to rotate by a very small angle. But if that angle could be measured, Cavendish could calculate the gravitational force between the spheres. From there, he could derive the gravitational constant and finally calculate the mass of the Earth. Imagine the difficulty of this experiment. The gravitational force between the spheres was so small that a light breeze, a vibration on the floor, or even a change in room temperature could distort the result. Cavendish had to work under extremely careful conditions, observing the tiny movement of the device and calculating with the most precise methods available at that time. The result was extraordinary. For the first time in history, humanity not only knew how the Earth pulled objects downward, but also estimated the mass of the planet itself. The Cavendish experiment is often called the experiment that weighed the Earth, although in reality he measured the gravitational constant and from that derived the mass of the Earth. From that moment on, a question that once seemed impossible had a scientific answer. The Earth was no longer just the ground beneath our feet. It became an object that could be measured, calculated and understood through the laws of physics. Today, with modern measurements, the mass of the Earth is determined to be about 5.97 times 10 to the 24th power kg. This is a number too large to imagine. Written out completely, it would be 5.97, followed by 24 zeros. Simply reading this number is enough to make us feel overwhelmed. To make it easier to imagine, let's compare. A car weighs about 1,500 kilograms. A skyscraper may weigh hundreds of thousands of tons. A large mountain may weigh trillions of tons, but all of those things are still extremely tiny parts compared to the Earth. Even all of humanity, all cities, vehicles, structures, ships, and machines that we have ever built occupy only an incredibly small fraction of the dead planet's total mass. Most of the Earth's mass is not on the surface, but deep inside. The crust where we live is actually only a very thin layer. Beneath it is the mantle, which occupies most of the planet's volume. Even deeper is the Earth's core, composed mainly of iron and nickel. Although the core does not occupy most of the volume, it is very dense, and therefore contributes greatly to the total mass of the Earth. This is similar to an egg. The outer shell is very thin. While the inside accounts for most of the mass. With the Earth, we live on the outermost layer. But the part that truly determines its mass lies in places we have never directly set foot on. And this enormous number is not just for making an impression. The mass of the Earth determines many important things. Whether gravity is strong or weak, whether the atmosphere can be retained or not, whether oceans can exist or not, and ultimately whether life can develop or not. Now let's imagine that the Earth were much lighter than it is today. If the mass of the planet became smaller, gravity would also become weaker. In that case, everything on the surface would be lighter. You could jump higher. Objects would fall more slowly, and the feeling of walking would be like being on a smaller planet. It may sound interesting, but the consequences would be very serious. If gravity were too weak, the Earth would have difficulty holding on to its atmosphere. Gas molecules could gradually escape into space. As the atmosphere became thinner, surface temperatures would fluctuate more violently. Days could become very hot. Nights could become very cold. And liquid water would also have difficulty remaining stable for long periods. We can look at Mars to understand this. Mars is much smaller than Earth, with a mass only about 1/10 that of Earth. Because gravity is weaker, this planet cannot retain a thick atmosphere like Earth. As a result, today Mars is cold, dry, and has a much harsher surface than our planet. If Earth were significantly lighter, it might no longer be a blue world with oceans, clouds, and abundant life. It could become a barren, cold, and much less habitable planet. That shows that the current mass of the Earth is not a random detail. It is one of the important conditions that help this planet become the home of life. Conversely, imagine the Earth becoming heavier than it is now. If the mass increased but the size did not change much, gravity on the surface would become stronger. Then our bodies would feel heavier. Walking, running, jumping, or even standing upright would require more effort. Large animals might find it difficult to exist. Plants might have to grow in lower and sturdier forms to resist stronger gravity. If the Earth were much heavier, the atmosphere might also become denser. Air pressure on the surface would increase. Storms, air currents, and weather could operate in completely different ways. The oceans would also be affected more strongly, and the geological structure inside the planet could change. A heavier Earth might also retain more gases, including gases that make the greenhouse effect stronger. If this process went beyond balance, the planet could become much hotter. In an extreme scenario, a planet with a large mass and a thick atmosphere could become a suffocating, hot world, unsuitable for life as we know it. This shows that the Earth lies in a very special balance. It is heavy enough to retain the atmosphere and water, but not so heavy that it turns the European enough to retain surface into an overly harsh environment. That balance has helped the oceans exist for billions of years, kept the climate relatively stable, and created conditions for life to evolve. In other words, the mass of the Earth is not just a number in textbooks. It is part of the formula that creates a living planet. Another interesting question is whether the mass of the Earth remains fixed forever. The answer is not completely. Every day, the Earth both gains additional material from space and loses a small amount of material into space. From outside, cosmic dust, small meteorites and fragments of interplanetary material continuously fall into the sad atmosphere. Most of them burn brightly as meteors before reaching the ground, but their material still becomes part of the Earth. Over very long periods, this amount of material also becomes significant. Conversely, the Earth also loses a small amount of light gases from the upper atmosphere. Atoms such as hydrogen and helium can reach enough speed to escape the Earth's gravity and fly into space. In addition, humans launch satellites, probes and rockets away from the Earth. But compared with the mass of the planet, this amount of material is almost negligible. Therefore, the mass of the Earth does change, but very slowly and by a very small amount compared with its enormous total mass. In everyday life, that change has almost no obvious effect. However, scientifically, this reminds us that the Earth is not an unchanging sphere. It is constantly exchanging matter and energy with the surrounding space. Our planet is rotating, gradually cooling inside, receiving cosmic dust, losing some light gases, and constantly changing over millions and billions of years. When we talk about how much the Earth weighs, we are talking about a very large number, but also a number that belongs to a world that is always in motion. So how much does the Earth weigh? The answer is about 5.97, 10 to the 24th power kilojoule. But what is astonishing is not only that number. What is more astonishing is that humans discovered it without placing the Earth on any scale. We weighed the planet by observing gravity, through delicate experiments, through mathematics, and through the ability to ask questions. From a falling apple, through mathematics and through the ability to ask questions. From a falling apple, a falling stone, or the feeling of our feet standing firmly on the ground. A falling stone, or the feeling of our feet standing firmly on the ground. Scientists followed the traces of gravity to understand the mass of the entire world. That number also shows us how special the Earth is. If it were much lighter, it might not be able to retain the atmosphere and oceans. If it were much heavier, the surface environment could become much harsher. The current mass of the Earth is an important part of the balance that helps this planet become the home of life. And the next time you walk on the ground, the home of life. And the next time you walk on the ground, remember that beneath your feet is not just soil and rock. It is an enormous planet, weighing nearly 6 sextillion kilograms, quietly spinning in space, holding us with gravity and protecting life with its very mass. You can also leave a comment below. In your opinion, which scientific question about the Earth is the most interesting? Thank you for watching and see you again in the next video.